Related rates can be tough. When we solve related rate problems, what we're doing is we're starting with some formula or equation, usually from geometry or trig or something that's just given in the problem, or a variation, something like that. But there's a lot of things for us to pull from, and then we have to differentiate with respect to a new variable. We have to identify what in the problem is constant, what is changing, what's a rate. Do substitution. Sometimes we're solving a derivative equation and a geometry or trig equation at the same time, and then put all that together to answer a question, okay? So there's a lot that is going on in here, so I want to give you a quick introduction to this first that's a little bit slower than the intro that we'll get when we do the live class, all right? So I have an equation here, okay, and the question asks me to differentiate this with respect to x, all right, which we've been doing that. We've been doing implicit differentiation because y is not isolated. So we are going to take the derivative with respect to x of this equation, and that's going to give us, actually, I'm not going to put an equal sign there, that's going to give us 2x minus 6y times y prime, which is also dy over dx. I'm going to use the Leibniz notation here on purpose, okay, and we'll see why in a minute, and then is equal to cosine of x. Now, if I want to solve for dy over dx, then I can do some rearranging. I can subtract 2x, divide everything by negative 6y, and I would have dy over dx, but for now I'm just going to stop right there, okay? Now, the second part of this says, using the same equation, now we're going to differentiate with respect to t. So when we are differentiating with respect to a different variable, we need to implement that chain rule, just like we did here with the y term. We need to implement that chain rule in any place where we have a variable that does not match the variable that is given right here. Okay, so let me rewrite this equation. We've got x squared minus 3y squared equals sine x. And now we are taking the derivative with respect to t, okay? T is representing time, as you'll see in the next example, okay? And when we do this, because each of these variables is not a t, we are going to take the derivative using the variables that are there, but we're going to attach d of whatever over dt, just like over here we have a dy over dx attached to it, okay? So this is going to give us 2x times dx over dt minus 6y times dy over dt is equal to cosine of x times dx over dt. Okay, now I'm not solving for any particular derivative. I'm not solving for dy over dt or dx over dt. I'll use this equation with something else, but right now I'm just doing practice for writing this equation. Okay, and so I can stop there. But as you see, every variable, the x here, the y here, and the x here, has a d of that letter over dt attached to it. Okay, so let's look at another example. We're given that B and H represent the base and height of a rectangle such that both are changing. Okay, so the base and height of the rectangle are changing, and the rectangle's perimeter remains constant. We want to write an equation that describes the relationship between the rates of change of both base and height with respect to time t. Okay, so this is what we have. We have base and height that are both changing, and a perimeter that is constant. So let's start with the formula from geometry that represents perimeter in terms of base and height. All right, so that's P equals 2 times base plus 2 times height. Okay, and then because we want to write an equation that describes the rates of change, okay, we are going to differentiate. We are going to find a rate of change. So we're going to differentiate with respect to t this entire equation. Okay, so we're taking the derivative with respect to time t. So because p is a constant, the derivative of a constant is 0. So I can replace this d over dt of p with a 0. And then over here, because these two are variables, I'm going to have 2, so derivative of 2b is 2 times db over dt, plus 2 times, again, h is a variable, dh over dt. Okay? And then this is the equation that relates the rates of change of the base and height. Now, could we divide everything by 2? Yes, we can. Can we move something to the other side? Sure, but for now we're going to go ahead and just stop here. Okay, so again, we're taking the derivative with respect to t of some formula, in this case, the perimeter of a rectangle. And again, p is, we're not replacing perimeter with 0, but since perimeter is constant, the rate of change of perimeter is 0. Okay, let's do one more. X and y are functions of time t such that the product of x and y is constant. Write an equation to model the relationship between the rates of change of x and y. Okay, so the product here of x and y is constant, meaning we can start with an algebraic equation, x times y equals, and it doesn't tell us what to use. I'm going to use k because k is a common letter for a constant. All right, so just make a note here. So x times y equals k, where k is a constant. Now I want to model the relationship between the rates of change again. So I'm going to take the derivative with respect to time, because we're functions of time t, of this entire equation. All right, now over here, I do have two variables being multiplied, so I need to use the product rule. So that's going to give me x times, and then the derivative of y with respect to t would be 1 times dy over dt, plus, and then y times, and the derivative of x would be 1 times dx over dt, okay, equals, and again, k is a constant, the derivative of a constant is 0. So we don't have to put dk over dt because dk over dt is 0. And this is our equation.